Push the throttle too fast. The engine cuts out. Instantly. Stay in the air a few hours. The turbine starts to wear down. Fire the guns, and the exhaust rolls forward, straight into the intake. Now you're flying close to 900 kilometers per hour. There's no margin left. One mistake.
Irgendwie
Flight
so schön
is
leise.
over. No warning. No recovery. Pilots were dealing with this every time they took off. These weren't stable systems yet. They were still being figured out while already in combat. That's where the jet age really started. Speed went up. Tolerance dropped. What people usually remember is the speed. The numbers. The shape. How different these aircraft looked. That part is easy to see. What matters more shows up later, when something goes wrong. An aircraft can be fast on paper, but if the engine only holds together for a few dozen hours, that speed doesn't carry very far. This comparison stays close to that reality. 3 early jet designs, placed in the same frame: the Messerschmitt Me 262, the Lockheed P-80 Shooting Star, and the MiG-9. 3 countries. 3 different ways of solving the same problem. We're not staying at the surface. This goes into how these aircraft actually behaved, how the wings handled at speed, what the engines could tolerate, what materials were available and what wasn't, and how those limits shaped what pilots could actually do in combat. By the time you line them up like this, a pattern starts to form. Germany pushed for performance, while running out of the materials needed to support it. The United States built around consistency and the ability to produce at scale. The Soviet Union moved fast, using whatever was available and accepting the risks that came with it. Those choices stayed with the aircraft, in how often they could fly, how they responded under stress, and how likely they were to make it back. Put all 3 into the same fight, under real conditions. Which one holds up? And once you answer that, the next question comes naturally. Do we still see the same trade-offs today? If you want to understand how technology actually translates into results in combat, stay with me. We'll break it down step by step. By 1944, as the Me 262 is no longer being built in open factories. Production is pushed underground, into sites like Wolpersberg and Bergkristall in Austria. Entire assembly lines are moved there, deep enough to stay out of reach of bombing runs. Inside those tunnels, the work continues without interruption. The space is narrow. Ventilation is limited. Output is expected to stay high. Most of the labor force comes from prisoners. Tens of thousands cycle through. The average time they last in that environment is short, around 6 months. The aircraft coming out of that system is all ready and operating close to 900 kilometers per hour. At that speed, the engine sits in a temperature range where material quality becomes critical. The alloys normally used for turbine blades are no longer available in sufficient quantities. Nickel, cobalt, molybdenum, all of them are restricted. The engine is built with what remains. Mild steel, coated with aluminum. Turbine blades hollowed out so air can pass through and carry heat away. The engine runs. Then it begins to wear. Operational life stays low, often measured in tens of hours. Heat builds up. Metal starts to deform. Failures show up early. The aircraft stays fast. The engine does not stay with it for long. In the United States, the jet program moves forward under a different set of conditions. By early 1943, intelligence has already confirmed the German work on jet aircraft. The requirement becomes clear. A jet needs to be built. The project is assigned to Lockheed. Kelly Johnson organizes a small team. Around 128 engineers and technicians. Work moves through direct communication. Decisions are made without long delays. The facility used for development is temporary. Wooden structures, a borrowed circus tent, located next to a plastic factory. The environment is not ideal. The process stays controlled. From initial design to a working aircraft, the XP-80, the prototype is completed in 143 days. The aircraft enters testing within a range that the system can support over time. Materials, manufacturing, and operations stay aligned closely enough that the aircraft continues to perform across repeated flights. At the end of the war, jet development in the Soviet Union is still behind. Time is limited. Captured German technology becomes part of the process. The BMW 003 engine is taken apart, studied, and adapted into what becomes the RD-20. Development moves forward from that point. On April 24, 1946, the two prototype aircraft are ready on the runway. One from Yakovlev, one from Mikoyan Gurevich. Both are prepared for flight. The order is decided by a coin toss. Mikoyan's aircraft takes off first. That aircraft later becomes the MiG-9. And the program continues from there. When these aircraft enter service, the conditions they were built under remain with them. Engine life varies. Response under load varies. Behavior over time does not stay the same across all three. At higher speeds, small changes show up quickly. Once a system moves outside its stable range, the margin is narrow. In that phase, recovery depends on how much time is available. Often, there isn't much. The next section looks at how those differences appear in the air. The wing on the Me-262 ends up where it is for a reason that shows up late in the process. The aircraft is not drawn that way from the beginning. Early layouts followed the same straight wing approach used across most fighters at the time. That changes once the engines are installed and the weight moves forward more than expected. The Jumo 004 is heavier than planned, enough to shift the center of gravity into a range where the aircraft no longer feels stable in flight. At that point, redesigning the entire airframe is no longer an option. So the adjustment happens at the wing. The outer sections are swept back by 18.5 degrees. The immediate goal is, on balance, keeping the aircraft within a controllable range so it can actually be flown. Once that change is in place, the aircraft behaves differently at higher speed. Airflow holds longer across the wing before compressibility effects begin to build. The critical Mach number moves closer to 0.86, and the aircraft continues accelerating toward roughly 900 kilometers per hour without the same drag increase seen on earlier straight-wing designs. The wing carries that benefit into flight. The rest of the system still has to keep up with it. The P-80 follows a more direct path. The wing remains straight, and the limits show up earlier as speed increases. The aircraft stays below that higher compressibility range, with top performance sitting around Mach 0.76. Inside that range, behavior remains consistent. Acceleration builds in a predictable way. Control response stays steady. Climb rate holds near 4,580 feet per minute, roughly 23 meters per second, and it stays there across repeated flights. That consistency becomes easier to notice over time. The wingtip tanks stay mounted during operation. They extend range, but they also affect how the wing carries load. airflow near the tips stays more controlled, and the aircraft maintains a stable roll response during maneuvering. The handling doesn't shift much from one engagement to the next. The engine starts to define how long each aircraft can stay in that performance range. The Jumo 004 is built as an axial flow turbojet, keeping the engine narrow and aligned with the airflow through multiple compressor stages. The layout works cleanly on paper, especially at higher speeds. In operation, the limits come from somewhere else. Material strength becomes the constraint. The alloys normally used for high-temperature sections are no longer available in sufficient quantity. Nickel, cobalt, molybdenum, each one affects how long the engine can hold together under heat. The structure is adjusted to keep the engine running. Mild steel replaces what is missing. Aluminum coatings are applied. Turbine blades are hollowed out, with air forced through them to carry heat away during operation. The engine produces thrust. It does not hold that condition for long. Operational life stays within 10 to 25 flight hours. After that, heat stress builds, the metal begins to change shape, and structural failure starts to appear. Throttle response adds another layer to it. Fuel flow increases quickly. Airflow takes longer to stabilize. Under rapid throttle, on input, combustion can become unstable. Temperature rises sharply, and the engine can flame out. At around 800 kilometers per hour, the aircraft continues forward while thrust drops off. The sequence moves quickly from input to failure. The Allison J-33 follows a different internal layout. Air is compressed outward through a centrifugal stage before entering combustion. The engine body is larger, but internal stresses are distributed in a way that holds over time. Material quality stays consistent across production. The engine continues operating across hundreds of hours. Throttle input remains, but manageable, even under pressure, and the engine stays within a stable range through repeated use. The aircraft returns from flight in the same condition it left in. At that speed, the sequence is short. The throttle moves. The engine response lags. Temperature rises faster than the system can stabilize. If the airflow breaks down, thrust drops immediately. Altitude starts to fall. There's no ejection seat in these aircraft. No extra margin built into the system. The pilot is still inside the same sequence, moving forward at speed while the engine is no longer responding the way it should. Everything that happens next fits into a very small window, and that window closes quickly. Speed brings the aircraft into position. What happens next depends on how the weapon behaves once the pilot commits. The Me-262 enters combat with a very specific task. It goes after heavy bombers. Aircraft like the B-17 are built to take damage and keep flying. Hitting the target is not enough. The hit has to end the engagement quickly. The aircraft carries 4 Mk-108 cannons, 30mm, mounted in the nose. The rounds are high-explosive Meiningeschoss. When they detonate inside the airframe, the structure doesn't hold for long. 3 or 4 hits are often enough to break a bomber apart. The result is immediate once the rounds connect. Getting to that point is where the constraint sits. The muzzle velocity stays around 540 meters per second. The rounds travel slower, they drop more, and the pilot has to close distance further than expected, especially with the aircraft already moving past 800 kilometers per hour on approach. The time available shrinks. From the moment the aircraft lines up, the window to fire and disengage can drop to 2 seconds or less before the closure rate carries it past the That timing stays tight through the entire engagement. There is no space to correct once the pass begins. The P-80 carries a different type of weapon system into the same phase of the fight. 6 M3 machine guns, .50 caliber, mounted in the nose. The muzzle velocity sits closer to 880 meters per second. The rounds reach the target faster, and the trajectory stays flatter. The pilot holds the trigger longer, up to 24 seconds of sustained fire. That time changes how the engagement develops. Tracking continues while the aircraft moves. Corrections happen during the firing run. The pilot stays in the engagement longer instead of committing everything to a single short pass. Across multiple engagements, that behavior stays consistent. Once both systems are in use, the difference appears in how the fight unfolds. One aircraft commits, fires, and exits within a narrow window. The other stays engaged, adjusts, and continues applying pressure while the geometry shifts. The gap between those two approaches becomes more visible when the target is no longer a bomber and starts maneuvering in return. The limits of these systems do not stay in the design phase. They show up in operation. August 6, 1945. North Hollywood, California. On the same day Hiroshima is struck, a test flight takes place under routine conditions. Major Richard Dick Bong is in a P-80. 40 confirmed victories. Experienced pilot. Familiar with high-performance aircraft. Shortly after takeoff, the main fuel pump fails. There is a backup system. The procedure is known. The cockpit is new. Layout is different. Time is short. The switch does not happen. The engine shuts down. The aircraft is still at low altitude. Ejection is initiated. The parachute does not have enough time to deploy. The sequence completes within seconds. There is no point in that sequence where the system pauses. The same, odd kind of constraint shows up differently in the MiG-9. The aircraft carries a 37mm N-37 cannon mounted in the nose, positioned between the engine intakes, along with 2 additional 23mm cannons. The layout keeps firepower centered. Accuracy stays aligned with the aircraft axis. At altitude, around 7,000 meters and above, the conditions change. Air density drops. When the cannon fires, exhaust gases build up in front of the intake. They do not disperse quickly. The engines begin to lose stable combustion. Airflow breaks down. Both engines can flame out almost immediately after firing. The weapon is still working. The propulsion system is no longer stable. A deflector is added. A rectangular plate, often called the butterfly, mounted at the muzzle to redirect gases away from the intake. For a period of time, it reduces the problem. After roughly 800 rounds, the structure begins to fail. The plate breaks under stress. Fragments are pulled into the intake. Damage moves directly into the turbine section. The aircraft returns to the same condition. The system operates. Then it destabilizes. Across these aircraft, the pattern stays consistent once they are pushed close to their limits. At lower speeds, mechanical issues can be managed. At jet speeds, the same issues compress into a much shorter sequence. The system moves from normal operation to failure without much transition in between. There is no delay built into it. Everything happens inside the same forward motion. And once that sequence starts, it carries through to the end. By the final phase of the war, the Me-262 has already proven what it can do in the air. The speed is there, the climb is there, and in the right conditions it can reach targets that earlier aircraft simply cannot touch. But the system around it is no longer moving at the same level, and that difference starts to show up quickly once you look beyond the aircraft itself. Production reaches more than 1,430 units, which suggests scale on paper. But in operation, the number that can actually take off at any given time rarely goes beyond 50, and that gap carries more weight than the total output number ever will. Fuel becomes one of the first constraints that fully surfaces. Shortages reach a point where aircraft are sometimes pulled out to the runway by horses just to conserve what little aviation fuel remains. And at that moment, the aircraft still has its performance, but getting it into the air becomes the real limitation. Once that condition settles in, the way it is engaged begins to change. Allied pilots stop trying to meet it where it is strongest and instead stay near the airfields, watching the pattern and waiting for the moment when the aircraft commits to landing. Landing gear extends, flaps come down, speed drops, and the aircraft moves through a sequence that does not leave much room to maneuver. That sequence is enough. One pilot describes it simply: meat on the table. The aircraft still carries speed, but it no longer has the conditions required to use it when it matters. The P-80 follows a different timeline. It does not enter combat during World War II, with only a small number of prototypes reaching Europe before the war ends, and at that point, the aircraft is still new inside the system. When the Korean War begins in 1950, that position changes. The aircraft is operational, redesignated as the F-80, and now part of a force where jet aircraft are already integrated into combat rather than being tested at the edge of it. On November 8, 1950, an F-80C flown by Russell Brown engages a MiG-15 and scores one of the first recorded jet versus jet victories. And from that point, the aircraft continues operating as the environment around it shifts. Newer swept-wing designs begin to take over air superiority roles, pushing into higher speed and altitude ranges, and the P-80 no longer sits at the front of that transition. Its role moves. The aircraft goes into ground attack, carrying bombs, rockets, and napalm, flying repeated sorties at lower altitude, where the demands are less about peak performance and more about how consistently the system can keep operating. Over time, that consistency becomes visible. The aircraft flies, returns, and flies again. The structure holds, the engine holds, and the system continues to function under load across repeated use. That is what keeps it in service. From there, the design continues forward into the T-33, with more than 6,500 units produced, used across multiple air forces to train pilots who will later move into more advanced aircraft. The aircraft stays in the system longer than its original role. The MiG-9 enters service under a different kind of pressure, filling a gap at a point where jet capability is still being established, and time does not allow for a longer development cycle. Production reaches more than 610 units, with some aircraft transferred to China in 1950 for air defense, and for a period of time it operates within that role. The limits remain. When the MiG-15 enters service, the shift happens quickly. Speed increases, altitude increases, and the overall performance moves into a different range that the MiG-9 doesn't stay within for long. The aircraft leaves that frontline role. The system continues forward without it. Across all three aircraft, the pattern does not sit in a single moment. It builds over time, through how often the aircraft can be used, how many are available at once, how many return, and how many can be sent back into the air the next day without interruption. Some designs reach higher performance early and carry that advantage for a short period. Some stay within a range that, or can be sustained over many flights. Some move forward quickly, fill a role, and then give way when something more complete arrives behind them. Those differences accumulate quietly. Not in one engagement, but across many. And over time, the aircraft that continues to operate stays in the system, while the one that cannot gradually disappears from it. By the end of this comparison, the outcome is no longer about which aircraft looks more advanced or which one reaches a higher speed on paper, because those metrics only tell part of the story and often hide the conditions that actually decide whether a system works or fails. The Me-262 clearly pushed aviation forward. It introduced ideas that would define the jet age. But it was built inside a system that could no longer support what it had created. That gap proved fatal. The MiG-9 tells a different story. It reflects urgency, a need to move forward quickly, even if the solution is incomplete, even if the system is not yet stable. It served its purpose, but only for a short time. The P-80 followed a quieter path. It did not dominate every category. It did not redefine aerodynamics in the same dramatic way. But it held together. And in the end, that was enough. This is where the historical story connects directly to the present. Because the pattern you see here did not disappear with the first generation of jets. It repeated itself. Look at modern air power, and the same tension is still there, just expressed through different technologies. Advanced fighters promise extraordinary performance. Stealth, supercruise, sensor fusion. Capabilities that look overwhelming when reduced to specifications. We have seen this before. A system can lead in performance and still struggle if it depends on fragile supply chains, complex maintenance, or limited production capacity. Once those constraints appear, the advantage becomes harder to sustain. That's the part people often miss. Because in real operations, an aircraft is not judged by what it can do once. It is judged by how often it can do it. How many can be produced? How many can be kept operational? How many can take off again the next day? That is where outcomes are decided. The lesson is not abstract. It is consistent across time. A system that is available, reliable, and repeatable will outlast one that only performs at the edge of its limits. And when that system is scaled, it becomes decisive. That's what this comparison really shows. The P-80 helped open the jet age for the United States. It proved that the system could work. But that confidence didn't last long. Because not long after, over the skies of Korea, a new aircraft appeared. Faster, more aggressive, built for a different kind of fight. The MiG-15. And the balance shifted almost overnight. How did a system that was still catching up with the MiG-9 suddenly produce an aircraft that challenged the entire U.S. Air Force? That's the next story. Click on the video on your screen and see how that fight unfolded.